The search for alien life, or at least planets with the potential to harbour life, has had a rocky ride since the James Webb Space Telescope, or JWST for short, came onto the scene. In the 2 or so months since the first images were released, JWST has broken and rebroken records in space imaging and discovery, from Mars to potentially habitable exoplanets to the most distant star we've ever seen. JWST seems to have it all, and to be honest, it can be quite hard to keep track of. And that's where I come in. In this video, I'm going to be talking about some of the key recent milestones in the search for alien life and habitable exoplanets, discussing JWST's recent images of Mars and the turbulent will they won't they of exoplanets and the life harbouring debate. Welcome to Brain Noises. I am Chloe, science communicator and recovering physicist, and on this channel we talk about the thoughts that pass through my mind, generally relating to science, but I cannot make any promises. So sit down, buckle up. Actually, no, it's going to be more relaxing than that. Sit down, grab yourself a cup of tea. Let's talk about space. The discussion around habitable planets would not be complete without mention of our nearest and dearest, Mars. A few weeks ago, JWST released its first images of Mars, capturing information about the planet's atmosphere that previous images have never done before. This data will help astronomers identify phenomena and gases that we just couldn't detect or see before. A part of what makes JWST unique is its ability to see in infrared. It was specifically designed to see in infrared, and it's why we're able to see some of the gases and the phenomenon that we weren't able to see with previous telescopes. So it's this feature that's making a lot of these new discoveries possible. Geronimo Villanueva at the NASA Goddard Space Flight Center in Maryland said, "Now you can actually get these full images of the planet in the whole infrared range at incredible sensitivities." Specifically, these recent images show the eastern hemisphere of Mars in 2 different infrared wavelengths. The shorter wavelength is a result of reflected sunlight revealing surface features often seen in the visible light images that we have seen, while the longer wavelength image reveals information about heat emitted from the Martian surface and atmosphere, as well as the concentrations of carbon dioxide in the atmosphere. An important thing to note is that JWST is designed to look at really distant, dim things. Think about those first images that were released. They were of incredibly far away things, and although Mars doesn't necessarily feel that close to you or I, in space terms, it's a very near neighbour. So imaging Mars, which is relatively close, is very difficult for JWST. And this is because the detectors are designed to pick up a very small amount of light from very far away things. So the sunlight that reflects off Mars, by comparison, is huge and just totally overloads the detectors. Think about what happens when you're in a dark room and someone suddenly turns the light on. Mars was particularly difficult to capture because of how quickly it's moving relative to what JWST is used to imaging. Mars moves very quickly around the solar system, whereas JWST typically images objects that barely move relative to other stars. Also, just imagine a car driving past you versus a plane flying in the sky. You know the plane is moving way faster than the car, but to you, from your perspective, it looks like it's going very slowly. So how were these images captured? The team of scientists had to adapt by taking short exposures and only sampling some of the light from the detectors. Team members talked about how excited they were by the quality of the data. It sounds like it was a very fingers crossed whether this really works type of situation because of the reasons I've just mentioned. And the thing is, this data doesn't reveal anything new about Mars. We already knew this stuff about the planet, so the dust, the surface rocks, atmospheric features like water and carbon dioxide, this is stuff we knew about. So what's so great about them? Why does it matter? Primarily, it's exciting because it serves as proof of concept. Collecting this type of data from relatively nearby planets is possible with JWST, and other telescopes just sort of can't collect this type of data. So we know lots of this stuff about Mars already, but just think about the kind of things that JWST might find out about the other planets in our solar system. Another exciting and very important element of this, so hold on tight, is that JWST can image the entire face of the planet at once in high resolution at a short exposure time, which allows for the study of things that happen in a short period of time, like dust storms, weather patterns. You can really have a proper look at the climate with this type of imaging. Typically, telescopes have such a long exposure time, so they point in one direction and sit there for a while, really taking in all the light. This short exposure time means that you can't really capture stuff that happens over a short period of time. An image taken over weeks will not be able to capture a change of daily weather patterns. I think this is a really cool point because when we think about telescopes, obviously we look at them through the lens of just normal cameras as mere humans who don't deal in telescopes. And so it's really easy to forget about stuff like exposure time. Obviously, photographers don't forget about stuff like exposure time. But when the camera shutter clicks, although it feels instantaneous because it's so fast to us, there is still a degree of time passing in which that camera is collecting light. And when you look into space, astronomers take advantage of this exposure time thing because they can just have an incredibly long exposure time, which allows for way more light to reach the detector. And you can then very cleverly manipulate the data to create an image from this long period of time, looking at averages and stuff. On top of that, back to the will it be suitable to harbour life, this full picture allows scientists to trace the origins of these gases found in really small quantities, which is really important for identifying biological and geological processes. Again, something we just haven't been able to do before, and something that then points to life and habitability. Habitability is the word I was trying to say. A, I'm not sure if that's really a word, could have just made it up, and B, what was the first word I said? Terrifying stuff. And so tracing these gases was just not possible with the small snapshots that we historically have been able to capture. Now let's talk about the recent exoplanet drama. In early September, 2 potentially habitable super-Earth planets were discovered. These 2 rocky planets orbiting the star LP8909, also known as Speculos 2, seem likely to be in the habitable zone, and one of them could be the second most Earth-like exoplanet discovered so far. Being in the habitable zone of a star means the conditions aren't too hot or too cold, so liquid water can exist on the surface. It's a bit of a Goldilocks situation. But let's not get overexcited. This is just a baseline, and in order to prove that these planets can actually harbour life, you need a lot more data, and scientists hope that JWST is the tool that will help us find that data. The next step, once we've identified planets in habitable zones, that's such a challenging word to say repeatedly, it's like a tongue twister. The next step is looking at the atmosphere, and that's exactly what scientists are trying to do with JWST. It's looking at the atmosphere, looking what's in the atmosphere, and similar to Mars, looking at, what the origins are of the things in the atmosphere, what's going on in there. So to find these planets in the first place, you need to understand what exoplanets are. For those who don't know, exoplanets are planets that are orbiting stars in other solar systems. So Mars and Jupiter are in our solar system. They're not exoplanets. Exoplanets are just all the other planets orbiting other stars in other systems. And the way we find them is by looking at stars and waiting for a dim, regular blip in the light that we get from them. And that is basically the planet passing in front of it. Like a hand passing close to a light. It'll cast a shadow that you then fall into. But as you can imagine, if a star is too bright, the light will I think a visual description of this will just be like the light sort of engulfs the thing moving in front of it, so it just doesn't have a significant effect and you won't be able to pick up on that blip. Imagine a pinhead in front of a light bulb. It just won't cast a shadow because it's way too small and the light is way too bright. And that's why a lot of exoplanet exploration looks at red dwarf stars, because they are a cooler and darker type of star. Another interesting point is that the habitable zone, it does change depending on the star's properties, but researchers hope that through observations with JWST they might be able to tweak this definition and gain a sort of further understanding of what might make a planet habitable. Finding out more about the planet's masses and their atmospheres, what kind of things indicate a habitable planet. So although we're kind of looking for this habitable planet, there is still a huge amount that we have no understanding of when it comes to habitability. Sorry. Absolutely crumbling here. And in this search for habitable planets, we are also refining our definition of what it means to be habitable, and we're refining our method of looking for these planets. And the coast isn't totally clear. Because habitable zones exist relatively near stars, because you need warmth for life, it can mean some planets can get caught out by solar weather events. And it was recently, like in the last few weeks, found that these planets get blasted by powerful solar flares, which may make them uninhabitable after all. And this is according to the largest ever survey of planet hosting stars. So It's quite a big deal. But again, like with everything, we're not really sure. There is a chance that these solar flares are actually a part of what makes a planet livable, and that the UV radiation from these blasts actually kickstarts life and the chemical processes needed to spark that first piece of life on a planet. All in all, nothing anywhere close to certainty has been established yet, and there's still loads of speculation on kind of both sides of the argument. Exoplanets discovered in this so-called habitable zone often have relatively short orbits around the star, so literally a matter of weeks or days. And the stars they orbit, the red dwarfs that tend to be a lot cooler and darker than our sun, can release powerful electrically charged particles in eruptions called coronal mass ejections, or CMEs. Earth-threatening CMEs from our sun are incredibly rare, but they do actually happen. One that was relatively recent, and the most powerful ever recorded at least, was called the Carrington event in 1859, and it caused telegraph communications around the globe to totally fail. A few people actually got electrocuted as well. It was pretty wild looking into it. And nothing has come close to that level since, but I mean, bear in mind that was less than 200 years ago, which is pretty small in Earth terms. But M-class red dwarfs, which is the stars that host most of the exoplanets we've found so far, could be prone to a Carrington-level event every few days or even every few hours, which does sound quite severe. I will not go into how they mapped out these solar events, but if you want to have a look, I've linked the paper in the description of this video. So while these frequent and powerful stellar eruptions could strip atmospheres or sterilize surfaces, there is also a chance that they actually kickstart probiotic life, as I mentioned earlier, just because of the high amount of UV energy that they contain. Alexandra Thompson at University College London says that the stellar flare catalogue provides an excellent overview of how energetic stellar flares may affect rocky terrestrial exoplanets, and it's useful for understanding their habitability. Understanding the host star well is extremely important for both current and future missions. So pretty mixed messages from the recent news surrounding exoplanets, but these kind of results, I don't really see them as a step back. And it is true that understanding stars and finding out stuff like this is a really important part of exploration. You know, it's not just about the pretty pictures, although they are nice to look at. So how close do you think we are to finding truly habitable exoplanets in terms of just years, or like what steps we need to do in between to work it out? It feels like we're at the incredibly early stages, and almost more importantly, what happens next? I don't know if it's going to be in my lifetime, but I do wonder, you know, if we find these planets, is it really going to be a universally good thing? I don't know. I'm actually a bit of a skeptic around this. I find this kind of stuff really exciting and really interesting, but when you consider the repercussions, I get a little bit scared. Anyway, that's all for today. Thank you for watching. I really appreciate the support. And if you made it this far, please let me know in the comments how well I did at repeatedly saying habitable. I give myself 10 out of 10. I'll be very upset if you give me any less than that. So choose your scoring wisely. Thank you for watching. I will see you in the next one. Goodbye.